Okay, today we are going to be solving a question graphically. The question says the number of atoms of a radioactive substance varied over a period of time as shown in the table below. Determine the half-life. Now, first of all, we're solving this graphically. How do I know that? Because they gave us a table. Now, to solve this graphically, we have to first of all know what graph is going to be. So it's going to be a graph of log n against time. Are you seeing that? A graph of log n against time. And then our slope will be equals to minus lambda over 2.303. And our intercept, from the last class I said so, and our intercept is going to be, what's our intercept going to be? Log n naught. Remember from the formula I gave us that log n equals to minus lambda over 2.303 t plus log n naught. I told us that this is our y, this is our m, this is our x, and this is our c. Do you remember that? I hope it's everybody that remembers that from the last class. Yes, I said it in the last class. Okay, so we're going to solve our graph based on this. But if you look closely, we have n, but it gave us what? Log n, abi? So now let's find log n from here. So we just take our calculator and punch for log n. Using our calculator, we get 3.70. we get 3.16. We go further to get 2.62, and then we get 2.08, and then we get 1.54. Now just punch your calculator and you should be getting this. Take log of 5,000, you get this. Take log of 1,450, you get this. Take log of 417, you get this. Take log of 120, you get this. Take log of 4.5, you get 1.54. Now that is the logarithm of everything. Then you go to your graph. Are you with me? Let's go to our graph. So stay tuned. Okay. Yes, this is my graph. So this is my graph. Let me draw out my grid lines. I'm using my biro. Please do not use your biro. I'm using my biro not because I don't have pencil, but because I want you to be able to see it clearly. Are we there? Yes, I want you to see it clearly. That's why I'm using my pen. So let me use my pen. So that line that I drew just now is for the y-axis. This line I'm drawing now is for the x-axis. I'll make sure not to ruin this, I promise. So yes, these are my values. This is my graph. Now, considering my values, I have 1.5, 2.0, 2.6, 3.6, and 3.7. Considering that, I can say that since the graph of log n against time, you first of all note that a graph of log n against time. I hope I'm seeing that. Yes, we are. Okay, and then y-axis is log n, abi? Y-axis is log n. But then look at what we have. We have 1.5, we have 2, we have 2.6, we have, I can basically use 2 centimeter to 0.5. So I can say that 2 centimeter to 0.5 units. What that means is that if here is 0, here should be, that's after this one, this next one should be 0.5. The next after this one should be 1.0. Then the next should be 1.5. Then the next should be 2.0. The next should be 2.5. The next should be 3.0. The next should be what? 3.5. And the last one should be 4.0. Are we there? See, it covers. Are you seeing that? You're seeing that it covers. It tallies very, very well. Now, what this means is that from here to here is 0.05. I mean, from here to here is 0.05. From here to here, that is, each box is 0.05. Do not forget. Now, let's look at the x-axis. The x-axis is t. This is our t. We have 0, 5, 10, 15. We can also say that 2 centimeter to 5 units. 2 centimeter to 5 units. So see, this is 0, so this is 5. This should be 10. This should be 15, and then this should be 20. But that looks quite small. So what should we do? If we say 2, 4, 6, 8, 10, 12, 14, 16, 18 to not reach. So I think this is better. Let's just leave it like this to avoid plenty errors. Let's leave it like this. So by using this, we'll try another graph later on, but we're using this for now. Okay, so let's just use this for now. So yes, using this, we know that according to the graph, we're using the graph. Don't forget, I don't know how we're going to see both at the same time, but I will try to make us see both at the same time. Okay, so let's do this. Please, in a way, I think you should try and know these values that we have here, and let's try and see what we have. So firstly, we have 0 to 3.7. See it? 0 to 3.7. So I'll come here, I'll locate, this is 0 is starting point. So what I have to locate now is 3.7. So this is 3.5, 3.55, sorry, yes, then 3.6, 3.65, 3.7. This should be 3.75. So this is 3.7. Here is 3.7. So I'm going to mark that. That's 3.7. Then we'll go to the next one. Next one says 5 to 3.16. Are you seeing that? 5 to 3.16. So we go. This is 5. This is 5. Now let's look for 3.16. This is 3.0. And this is where 5 is. 3.0, 3.05, 3.1, 3.15. So it should be around here. Yes, around there. So we'll move to the next one. Look at it. Next one is 10 to 2. Are you seeing that? The next one is 10 to 2.62. 10 to 2.62. Let's do that. This is 10. And then this is 2.5. From where 10 is, this is 2.5. Then 2.55, 2.6, 2.65, which should be in between here and here. So let's put this place as my 2.62. So move to the next one. The next one is 15 against 2.08. So let's try that. This is 15. That's 2 boxes away from here. It's 15 against 2.0. This is 15, and then this is 2.0, 2.05, and then the next one is 2.10. So it should be closer to the 2.10 than the 2.05. So that's why we have that. And then the last one is 20 against 1.54. So this is 20, I mean, and then this is 1.5. So 20, 1.5, count upwards, 1.55. So that's where 1.54 should be. So that's basically what you have. Are you seeing that? That's basically the line that you have. That's basically what you have. So that's basically what you have. So we're going to draw a line of gradients to join them all together. So looking at this, let's see the line that best fits. I think it should be, sorry, my ruler is not that long. My ruler is not so long, so I'm going to draw it anyhow my ruler gets it. I hope my ruler gets it right. So that's it. Sorry about the cancellation, but that's it. That's the graph. That's the graph. That's how it should look. So you know, as you can see, is a negative slope graph. Negative slope goes like this. Positive slope goes like this. So negative slope goes like this. Positive slope goes like this. So it's a negative slope graph. So you have to do your y2, your gradient. That's your slope. This is slope. M is slope. Slope is equals to what? Y2 minus y1 over x2 minus x1. I like to choose the first and the last. So on this part here, if you take this as your y2, this should be your x2. Then this as your y1, then this should be your x1. So I like doing that a lot. It's preferable and it's easier like that. So let's solve using that. Let's solve using that. I'm going to solve it here. So slope is equals to y2 minus y1 over x2 minus x1, which would give me let's say 3.70 minus 1.54 all over 0 minus 20. This should give us, let me calculate. Sorry, I'm calculating. I'm actually solving it the way I'm teaching you guys like this, just so people are seeing it very well. So 3.70 minus 1.54. That's 2.16 divided by minus 20. So So that should be divided by 20. So slope is equals to minus 1.0, sorry, slope is equals to minus 0.108. That's our slope, and that is in per minute. So this is our slope. But don't forget, I also said this about slope. Abi, are you seeing that? I also said this about slope. So with that, you can say that since slope is equals to minus lambda over 2.303, it should now be minus 0.108 equals to minus lambda over 2.303. Minus should cancel minus. So lambda should be equals to 2.303 times 0.108. And our final answer should be 0.249. So that's 0.249, also in per minute. Also in per minute. Are we there? Also in per minute. Now, I've gotten slope. Don't forget that lambda is the same thing as 0.693 over half-life. And the question said that what? We should determine the half-life of the radionuclide. So I've already gotten lambda. It's very, very easy now. So we can just say that half-life is also equal to 0.693 over lambda, right? Yes, right. So let's do that. So since 0.693 over lambda will give us half-life, so that should be 0.693 over 0.249, which will be what? Which is 2.78 minutes. So that's our answer, 2.78 minutes. Are we there? Did we get that right? I hope you did. We're going to try another question, but I don't know. Should we try it now? No, let's not try it now. We'll try it later. That one is on activity. So let's start a new topic. We're going to start a new topic. Okay? Let's start a new topic. The next topic is activity. Activity and mass. Yes, that's the next topic. If you've not seen activity and mass, now you have it. So activity and mass. What is activity? What is activity? First of all, activity is the number of disintegration per unit time. Does that not sound familiar? I think that sounds familiar. It says number of disintegration per unit time. So they're basically saying that activity is equals to the n over dt equals to, that's minus the n over dt equals to 1. So they're basically saying that activity is equals to, see that disintegration, that says number of disintegration per unit time. Disintegration per unit time. Are we seeing that? Yes, we are. So that's basically what activity is. I'm sorry, the camera is switching. Sorry. So that's basically what activity is. Activity is the number of disintegration per unit time, which is A equals to minus the n over the t. Do not forget that. Do not ever forget that formula. Remember this formula now. We used it in solving, in deriving, what's it called? Decay constant relationship with half-life. Yes, we used it in the last class. So yes, if that is so, I can basically say that A is equals to A naught e raised power minus lambda t. You know, in the other one we did n equals to n naught e raised power minus lambda t. So it's kind of like the same thing. So this, I just say this is an equation 2, and this is 1. Now the unit of activity is Curie. Are we there? The unit of activity is Curie. It's not Curie that they used to cook, but it's Curie. Yeah. It is Curie. And it's defined as the quantity of any radioactive nuclide. It is defined as the quantity of any radioactive nuclide. Are we there? I think so. So it's defined as the quantity of any radioactive nuclide in which the number of disintegration per second is 3.7 times 10 raised to the power 10 disintegration per second. So basically they are telling us that one Curie which is same thing as 1 Ci, is equivalent to 3.7 times 10 raised to the power 10 disintegration per second. What of 1 millicurie? Obviously 1 millicurie, I'm sorry I'm calling it curie, should be equivalent to 3.7 times 10 raised to the power 7 disintegration per second. You know, milli is times 10 to the power minus 3, so minus 3 from 10 give you 7. Now 1 microcurie, which is 1 microcurie, is equals to 3.7. That one is times 10 to the power minus 6, so 3.7 times 10 to the power minus 6 from 10 should give us 4 disintegration per second. Now the last one, 1 nanocurie, which is 1 NCI, should give us what? That's 10 to the power minus 9, so that should be 37 disintegration per seconds. So please make sure that you know this. Make sure that you know all of this that I am making mention of. Make sure that you know them. You need them in solving questions eventually. So just make sure that you do know them. So please make sure you know them. So moving on. Yes, let's move on. Now, we also need to know about specific activity. That's actually what we need. Specific activity. Now, what is specific activity? Specific activity is defined as the number of disintegration per unit time per gram of radioactive substance. So with that being said, I'm basically saying that specific activity is equals to activity over mass. That's all. So it's defined as the number of disintegration per unit time per gram of a radioactive substance. And we know that activity is the number of disintegration per unit time. So that's disintegration per unit time, that is disintegration per unit time, which is per seconds, then per gram. Are you seeing that? So specific activity is activity divided by mass. That's basically it. Basically activity divided by mass. It's not something you need to bother yourself with. It's not so difficult, is it? No. It's not difficult at all. Now that they have brought mass into the equation, there's some formulas that you should just know. They brought mass into the equation, so let's relate formulas together. Let's relate mass and half-life together, since they brought mass into the equation. Now, first of all, we know that A is equals to, are we saying this? Yes, we are. We know that A is equals to minus dN over dt, which is same thing as lambda n, abi? Yes, we know that. Abi? Yes, lambda n. If that is so, I can replace this as A equals to lambda n. This n is number of atom, right? This n is number of atom. Please take note, don't forget this n is number of atom. And we know that number of mole is equals to what? Mass. That is where mass comes in, over molar mass. I can represent this mass as small m, this molar mass as capital M, and this number of mole as n, right? I believe I can do that. With that being said, let's make mass the formula. So mass, or let's leave it like that. Let's do that first. First of all, another formula for number of mole. Number of mole, n, is also equals to number of atom, capital N, all over Avogadro's number. I don't know if I spelled my Avogadro well. Isha Avogadro's number, which is NL, represents as NL. Are we there? Yes, I hope we are there. Sorry. Yes, represents as NL. Now, if number of mole equals to mass over molar mass, and number of mole is also equals to number of atom over Avogadro's constant, we can just say this is equals to this. So with that, I can say that mass over molar mass is equals to number of atom over Avogadro's constant. Now let's make number of atoms simple the formula. So number of atom will be equals to cross multiply, that will be mass times Avogadro's constant over molar mass. Now I've got the number of atom, and I said it here, look at it, that A is equals to lambda over number of atom. So A equals to lambda times mass times Avogadro's constant all over molar mass. See, I've related, but remain to relate half-life. Now note that half-life is equals to 0.693 over lambda. We can also say that lambda equals to 0.693 over half-life. So we can substitute that here. So substitution that will be A equals to 0.693 over lambda times m times Avogadro's constant all over capital M. Now let's make this small m solve the formula by cross multiplying. M will be equals to, are we there? I hope so. Yes. M will be equals to, this m will be equals to cross multiply now. Wait first. When cross multiply, we have A times lambda times capital M, that's molar mass, which is equals to 0.693 times m times Avogadro's constant. So divide both sides by 0.693 times Avogadro's constant. So 0.693 times Avogadro's constant. So mass is equals to activity times lambda. No, lambda is not there again. Why am I saying lambda? This times. I'm sorry, there's no lambda there anymore. Lambda has gone. This should be half-life times half-life. I don't know why I'm writing it as lambda. I'm sorry, very sorry. This is half-life. This is half-life. Please correct my mistake. So times half-life, A times half-life times molar mass all over 0.693 times Avogadro's constant. I am not going to edit that part out. I made a mistake, and yes, I'm owning up to my mistake. So yes, this is how you use mass to solve question. Now you might be wondering, why am I deriving this thing for you? I'm deriving for so that you know how it was gotten, but you don't need to derive it in the exam more. As I derive it for you now, just put this formula in your head. You used to solve in the exam. Just cram it. You know now. You know how we used to do it. Just put it in your head. You used to solve question in the exam. So moving on. I'm moving on to the next one. If you need to go back, you can just rewind it. It's a video. It's not live. I'm not going live. It's just a video. So let's solve it. Now, first thing they ask you to find is what? Is the mass. And I told you guys that you can use the formula that mass is equals to activity times half-life times molar mass all over 0.693 times Avogadro's constant. Abi? Yes, that formula. But the first here is that we don't even have our half-life yet. We have our half-life. It was given in 19.9 years, but our activity was given in 0.5 millicurie, which equivalent to 0.5 times, what is 1 curie? 0.5 times 10 to the power minus 3 times, now 1 curie is 3.7 times 10 to the power 10. So this integration per second, meaning that since we have our activity in seconds, we have to convert our half-life to years. So let's convert our half-life to years. First of all, activity in seconds should basically give us, okay, we can leave this one like this. This should be the same thing as 0.5 times 3.7 times 10 to the power times 10 to the power 7 disintegration per second. So what we have to do now is convert our half-life to seconds. So 19.9 years to seconds should be 19.9 times 365 days. We have 365 days in a year. We have 365 days in a year, and each 4 years we tend to have a leap year. So because of that, you say 365 1/4, because we have 1/4. We have one out of 4 years now. We have out of 4 years we have 1 leap year. Out of 4 years we have 1 leap year. So because of that, you say 365 days times 1/4, because we can have a leap year in 4 years. So in each 4 years we have leap year. I hope you understand what I mean. So multiply by how many hours is in a day? We have 24 hours. How many minutes? How many minutes is in an hour? We have 60 minutes. How many seconds is in a minute? That's 60 seconds. When you match all of this together, you're supposed to get 6.27 times 10 to the power 8 seconds. Let's make sure you confirm yours. Make sure you confirm yours, please. Make sure that you're not just following me like that. Confirm. I might be wrong. If I'm wrong, call my attention to it. Just comment, bam, you are wrong, and then I will change it immediately. But please make sure that I'm wrong before you comment that I'm wrong. Don't gonna make people think I'm wrong when I'm not wrong. Okay, so confirm your own while I do mine. Sorry. So yes, I'm correct. So we've gotten our half-life. So mass is equals to activity, which is 0.5 times 3.7 times 10 to the power 7 times, let's put this integration per second, times the half-life 6.27 times 10 to the power 8 seconds. Seconds cancel seconds. Okay, so yes, multiply by that, then you multiply by 90. That's 90 is the molar mass, all over 0.693 times 6.023 times 10 to the power 23. So if you do your calculations right, if you calculate everything there correctly, you should be getting mass to be equals to 2.5 times 10 to the power minus 6 gram. So if you get this, you are correct. Make sure you punch your calculator right. Now, if you've gotten this, we go and solve the next question that says what is the specific activity of the sample? Specific activity, as I have said, is specific activity equals to activity over mass. So we have activity should be what? 0.5 millicurie, which is the same thing as 0.5 times 3.7 times 10 to the power 7 divided by the mass, which is 2.5 times 10 to the power minus 6. So SA, which is specific activity, is equals to 7.4 times 10 to the power 12 disintegration per seconds per gram. Per seconds per gram, that's it. So that's how you get the specific activity. So now the next question says that you should find activity after 30 years. Now don't forget that formula, the 2.303 log n over n naught. Now instead of using n over n naught, you use a over a naught equals to minus lambda t. Now the good part is that we can easily get lambda. We have half-life, but because they said after 30 years, you no longer need to convert your half-life to seconds. You now have to use the half-life in years. They give you your half-life as 19.9, so you use that half-life in years to get our lambda, and lambda is equals to 0.693 over half-life, which is 0.693 over 19.9. that should give you 0.696693 divided by 19.9. That should give us 0.03 So that should give you 0.0348. Yes, that's what it gives you. This is in per minute. Sorry, per hour. Per years. That should be in per years. So we have our half-life in per years. So now that we have our half-life, we have 2.303 log. You are looking for activity after 30 years. So it means that you don't know A naught. It means that you don't know A naught. But you know A. Yes, you know A. Now you might be wondering what is A. You actually know A. A is 0.5 millicori, and you have to leave your answer in millicori, or you can convert it to seconds if you like. But first of all, A is 0.5, so we're looking for A. So I would rather not use this formula. Are we there? I'd rather not use this formula. I would say you use the formula that says that use the formula that says A equals to A naught exponential minus lambda t. I think this formula should be better. Now you're looking for A equals to A naught is what? 0.5 millicori. Whatever you get now, you need to also be in millicori for A. So you don't need to convert millicori to disintegration per second. So 0.5 times exponential. That's exponential of minus 0.038 times 30 years. So that's A equals to 0.5 exponential minus 1.14. So let me see if my calculator can do that. Exponential minus, I know you should be getting A to be equals to 0.177 millicori. But if you want to convert it, you can now say A equals to 0.177 times 3.7 times 10 to the power 7, which will give you 6.5 times 10 to the power 6 disintegration per second. So the choice is yours. You either leave your answer in this or you put your answer in this, whichever one you like. So that's that. That is all. Now you can get more questions on the past questions that I dropped in the group chat. Yes, if you want to join the group chat, just DM, just say hi on the group, drop your number. Yes, that's preferable. Drop your number on the comment section, and then I'll add you up to the group chat. That's if you're not in the group chat. And if you're in foreign level and you're doing radioactivity, or you're in any level at all and you're doing radioactivity, you can ask me any question. I will be happy to answer your questions. Okay, so moving on. This is how you answer questions for specific activity. Now let's take a graph question again on activity. There's a graph question on activity. Let's just quickly take that question. All right? Yeah, let's do that. Okay, now that's the question we're taking. It says a radionuclide which was separated from its cyclotron target gave the following readings. As you can see, it says the time. That's basically what I'm about to write down for us now. So it says time 2 hours, count per minute. So this is an activity graph question. We are given A, as you can see. We are given A. This is A in activity. Now we have to find log A as usual. It's just like using the other formula of log n. So here we are doing log A equals to minus lambda over 2.303 t plus log A naught. So it's a graph of log A against, this is the slope, this is our x, and then this is our c. So we're plotting the graph of log A against t. Are you seeing that? So let's quickly take the logarithm of all what we have there. So we take log 3660, which should give us 3.56, 3.51, 3.41, 3.22, 3.03, 2.65, 2.17. So this is what we have. So we are here again. So this is basically what we have been given. So we're going to plot our graph based off on all this information that we have. So as usual, let's get our graph. Let us get our graph. Our graph is right here. So this is what we use for the graph. Now it's a graph of log A against t time. Are we seeing that? Yes, it's a graph of log A against time. Where y-axis, now look at the values we have. 2.1, 2.6 is 3.0. I'm thinking, I don't know if you're thinking with me, if I make it 0.4 units, this will be 0.4, 0.8, 1.2, 1.6, 1.6 plus 4 plus 0.4, that's 2, 2.4, 2.8, 3.2, 3.6 to reach. So let's do that. So that will be 2 centimeter to 0.4 units. So let's do that. So here we have it as 0.4. Here we have it as 0.8. Here it is 1.2. Here it is 1.4. Here it is 2.0. Sorry, 1.6. 1.6, then 2.0, then 2.4, then 2.8, then 3.2, then 3.6. Are you seeing that? So this is it. Now from here to here, that is each box. Are you with me? From here to here is 0.04. And let's look at our x-axis. I think on the x-axis we should just say 2 centimeter to 10 units. Yes, 2 centimeter to 10 units. So that will be 10, 20, 30, 40, 50, 60. I think that's best. Yes, that's perfect. So we're using this to plot our graph. Are we there? We're using this to plot our graph. Now, I don't know. Let's first try with this. So 3.76 against 2. Sorry, 3.56 against 2. Are we seeing that? 3.56 against 2. So let's look for 3.56. This is 3.2. So this should be 3. Count to me. 3.2, 3.24, 3.28, 3.32, 3.36, 3.4. After 3.4, let's go again. 3.44, 3.48, 3.52, 3.56. So this is where 3.56 is against 2. So this is, come here, this is 1, 2. If you count from here, 1, 2. So this is 2. So that's the first point we have there. Here. Now the second one is 4 against 3.51. Don't forget this is 3.56. Just go back down. 3.56 minus 4. That's 3.52. So 4 should be around here. Now the next one is 3.41 against 8. Now this is 3.4. Don't forget this is 3.4. And then let's see if we can find 8 here. This is 10. This line here is 10. From here to here is 10. So back by 2. 1, 2. Now let me show you. See it here. This is 10. 1, 2. This should be 8. So if you trace that up, you can use your graph to do it. Trace that up. It should be around here. And then it's 4, 1. So it should be around here. So that's that. The next one is what? 16 against 3.22. This is 3.2. Next box up is 3.24, which we are not going to. We are going to the middle of 3.2. But it says 16. So this is 10. This is 15. Then this is 16. So we should start with here 10. This is 10. This is 15. This is 16. So 16 should be around here. And the line is in the middle. So that's that. The next one, 24 against 3.03 against 24. So this is 3. This is 2.8. let's look for 24. This is 20, 21, 22, 23, 24. So tracing that up, it should be around here. This is 24. So let's get from here 2.28. That's 2.84, 2.88, then 3.02. And we're looking for 3.03. So we're on the right track. We're here. And then the next one, not the last one, 40 against 2.65. This is 40. 2.65. This is 2. The middle should be 2.6. So let's find 5. 2.6, 2.64. So 5 should be right above it. Now this is 2.4, 2.44, 2.48, 2.52, 2.56, 2.4. In case 2.6, in case you are wondering how I know. So the last one, 60 against 2.17. This is 60, and this is 2.0, 2.0, 2.04, 2.08, 2.12. Then 2.14 should be around the corner. 2.1 what? 2.17. So that's 2.1, 2. Let me go again. 2.0, 2.04, 2.08, 2.12, 2.16. So it should be around here. So that's it. That's what we have. Are you seeing the lines? Are you seeing it? That's all. So you now draw the line that makes all of them touch. I'm sorry that I don't have ruler. I don't have better ruler. I think it's still straight. Look at it very well. Don't judge me. I think it's still very straight, right? Yeah, I think so. So once again, it's a negative slope. Are you seeing that? It's like this. Negative slope is always like this. Positive slope is always like this. It's a negative slope. That means you are on track. Now, the question there, are we seeing it? The question says determine graphically the half-life of the radionuclide. Then the second question says, what is the initial? Are you seeing that? So determine graphically the half-life of the radionuclide and what was the initial activity in counts per minute. So first of all, let's determine graphically the half-life. To do that, you have to first of all find the slope. And don't forget, I told us how to get slope. Just take this as y2, take this as x2, and take this as y1, take this as x1. So that would be slope equals to y2 minus y1 all over x2 minus x1, which is 3.56 minus 2.17 divided by 2 minus 60. That will be 1.39 all over minus 58. That should give us slope to be equals to 0.02324. That's minus. So this is our slope. Now don't forget that note slope is also equals to what? Minus lambda over 2.303, which will now be minus 0.024 equals to minus lambda over 2.303. Minus cancels minus, so lambda is equals to 0.024 times 2.303. That will give us 0.055. That should give us 0.055. 552. Let's put it like that. I approximated. Don't ask me. I did not approximate in my calculation, but I approximated down here. So if you calculate your one and it's giving something different, just know that it's because of approximation issues. Okay, so let's continue. Now I've gotten lambda in per hours. Our lambda here is in per hours. So now that I've gotten lambda, you can get the half-life by saying what? Half-life equals to 0.693 over lambda, which is what? Which is 0.693 over 0.552. So I'm coming. Okay, which is equal to 12.6 hours. So that's it. That's what you get. Now, the next part of the question says that you should. He was asking what is the initial activity, Abi? Now, please come back to the graph. Come back to the graph. Now, let's find the intercept on the graph. Here is the intercept. Here is the intercept. Are you seeing that? This is intercept. And if I'm correct, let me help you zoom in so that you can see it as well. If I'm correct, look at it. If I'm correct, my intercept is 3.6, right or right? I'm sure that's right. My intercept should be 3.6. So if my intercept is 3.6, so let's take that. Intercept equals to 3.6. And don't forget, come back here. I told you that this is your intercept. So if log A0 is equals to 3.6, A0 is the initial. What do you have to do? You take antilog of A0. So antilog of A0, that's antilog equals to A equals to antilog 3.6. That should give you what your initial is. That's 3981.1 pounds per minute. So this is your initial. So that's all. Are we there? That's what they asked you to solve. So please. Thank you for watching. Thank you very much for watching. Please subscribe.